Find the mass of the region bounded by the upside down cone, z equals 5 minus root x squared plus y squared, and the xy plane. If the density is given by, density is 1 over 5 minus root x squared plus y squared. Those look suspiciously similar. Now, one thing that I notice is I see lots of x squared plus y squared, and we're in 3 dimensions. And when I see x squared plus y squared, if I was in 2 dimensions, I'd say polar. But because we're in 3 dimensions, we say cylindrical, right? So we say, okay, let's think of this in terms of cylindrical coordinates. Now that says, here we're thinking of z is 5 minus r. Now if you were to sketch this in the RZ plane, so here's r, here's z, well, you intersect up here at 5, and then you go down, and you intersect down there at 5. And now the xy plane, that's also known as z equals 0, that's here. And so, in terms of the RZ plane, we see a triangle. Say, all right, cool. Now, how do we form our solid? Well, we can spin it. So spin this triangle around the z-axis, and what we'll get is, as was mentioned, an upside down cone. All right, so we now have a really good idea of our region. And so we have it for 5. We're just going down, 5 in each direction. Okay, so there we go. Now, we don't exactly need to know, but it's good to have a good intuition of what our shape might look like. All right, with all this in mind, we can start to say, okay, what do we need? Well, we need to describe this in terms of polar, in terms of cylindrical coordinates. Now, if we think about what's going on, we can say mass is the integral, 3-dimensional integral, because it's a 3-dimensional solid, and over our region of density dV. Now, we're switching to cylindrical, so integral, give ourselves space. Our density, 1 over 5 minus r, and dV is r dz dr d theta. Well, what's true about theta? Well, theta, it's completely symmetric, and so theta, it's the full revolution, 0 to 2 pi. All right, well, what's true about r? Well, look in the RZ plane. Where do we go? R equals 0 to 5. All right, 0 to 5. Okay, now what's true about z? Well, if you go to any point, we go in between those two. Now, that's the xy plane down here, that's z equals 0, and we go all the way up to z equals 5 minus r. All right, good. Now, this is making us a little nervous, but that's okay. Let's go ahead and just follow the integral. And what do we get? Well, integral 0 to 2 pi, integral 0 to 5, and now we have this 1 over 5 minus r times z, because we're integrating with respect to z, and the r's are constant. We're evaluating from z equals 0 to z equals 5 minus r, and then we say, when you plug in 0, we get 0. When you plug in 5 minus r, you have a 5 minus r there. Whoa! It's like they planned for them to cancel because they did. They wanted cancellation. So this becomes 0 to 2 pi, 0 to 5 of r dr d theta. Now, we could keep integrating, or we could make a quick observation and say, well, wait a second. what is this? We're integrating in polar r d theta, and so we can say, oh, this is like the area of the region in the xy plane. So, okay, so what is that? It's the area of, if you come here to the xy plane, it's this area right here. So this is the area of a circle of radius 5. And we know how to find that area. And so this gives us pi r squared, or 25 pi. Now, if you just do the integrals, you'll get the same thing. And so, okay, not so bad, right? Not every problem that looks scary is scary. Just start and be careful and be methodical. Life is good. Good. All right. Consider a solid sphere of radius 8 entered at the origin. You know, I bet you that's a typo. So we're going to put centered. There we go. Centered at the origin. Use spherical coordinates to set up a triple integral giving the volume V of the cap, lying inside the sphere and above the plane z equals 5. You do not need to solve the triple integral. Okay, good, good. All right, so let's talk about our shape. We know it's a sphere and a plane, because those are the two things, right? Plane of 5, sphere of radius 8. So we should start by sketching, and just so we get a good intuition. So we'll have our sphere, and that looks a lot like a sphere. Okay, cool, 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 cool. All right, now then we have our plane, and all right, well, so we have our plane here. This is our plane z equals 5, and what will happen is that the plane will intersect the sphere, and what do we want? Well, we want to be inside the sphere, but above the plane. And so our region is this thing up here. All right, good. Now, how do we describe this? Well, let's make a couple of quick observations. First thing is, even though it says spherical coordinates, we can use a lot of the same ideas in cylindrical coordinates to help us out. We notice that there's this beautiful symmetry. So if you were to spin around the z-axis, the shape is maintained. Now what that's telling us is about theta. It says, oh, theta will always be, it's the same shape however you spin it. So theta is going the full circle. So that's a good thing to know. So 0 less than or equal to theta less than or equal to 2 pi. All right, so there's an easy thing for us to do. Now, what else can we do? Again, we can channel our cylindrical coordinates and say, let's look in a slice. It's essentially the same as our z-plane. So we're going to slice here, go straight down, and what will we see? Well, what we're going to see is the following. We're going to see our z equals 5, and that looks like a line. And then we're going to see our sphere, which will look like a circle. And so our three-dimensional solid, now it's more looks two-dimensional, is we have this lovely shape. Okay, good. Now, remember, we're in our spherical mindset, not our cylindrical mindset. And so we have to start thinking about our other parameters. So we talked about theta. Let's talk about our phi. So, how do you find phi? Well, the way we find phi is to say, well, what is phi representing? Phi is an angle. And so we say, okay, so we just have to figure out the right angle. And so phi equals 0 is straight up the z-axis. And so now what we do is we say, okay, where do we hit? Well, okay, we're still hitting, until we sort of stop right at that point, and after that, we don't hit anymore. So see how that's the origin? And we're just saying which angles do we hit our solid. And so we're going from this angle, where phi equals 0, to whatever this angle here is. All right, because phi comes off the positive axis. Now, how can we find that? Well, let's look at this triangle for a moment and say, can we notice anything? It's a right triangle. You know, it's not a wrong triangle. It's the right kind. All right, well, what else can we say about this? Do we know any of the sides? Well, sure. In fact, I can tell you two of the sides. I can tell you that this side, the hypotenuse, is from the origin out to the circle, which is really the sphere. So that's the radius. So that's an 8. This side is up to the plane. So that's the plane z equals 5. All right, so it's a triangle with 5 and 8. Now you might say, I don't remember triangles with 5 and 8. Well, yeah, not every triangle has beautiful numbers. That's okay. It still is a perfectly fine triangle. Now you might say, well, what can we say? Well, if this is our angle phi in the corner, what do we have? Well, we can say we know the adjacent side and the hypotenuse side. So we could say cosine phi is the adjacent side over the hypotenuse side, 5/8. So that says phi is, now take the arc cosine of that. Arc cosine of 5/8, which is arc cosine of 5/8. All right, but the punchline here is now we know, where does phi go from? So we can update and say, hey, we already did theta, and we just figured out that phi starts at 0 straight up and goes until this angle, arc cosine of 5/8. All right, now, rho. Okay, so let's stay in the same picture, even though it's getting a little bit crowded. And we say, okay, so now we're going to go and we start at the origin. So for spherical, it's how does everything relate to the origin? So theta and phi are giving you directions. Rho is distance. And so you come out from the origin and you say, okay, what do I hit? Well, I start when I hit this plane, then I continue until I hit the sphere. Now, the sphere, that's great, because what we have is, we're saying that for rho, we're going to go from the plane to the sphere. Now, we have to express this in terms of rho, phi, and theta. Well, for the sphere, that's not too bad, because it's a sphere. Spherical coordinates, spheres, should be pretty simple. And so that becomes, the sphere is just rho equals 8. Sphere of radius 8. Now what about the plane? Well, we see the plane here is z equals 5. And we say, great. No, that's z. We need rho, phi, and theta. In particular, we really need to get rho equals something. All right. Well, what can we do? Well, what's z? Z is rho cosine phi. And then we say, okay, so rho cosine phi equals 5. Well, great, but I need rho. So I need to move the cosine across. So, okay, so rho is 5 over cosine phi, which is the same as 5 secant phi. And now we're ready, right? Because we know where we're going from. We're going from the plane, which is 5 secant phi, to the sphere, which is 8. So that tells us that we're going 5 secant phi less than or equal to rho, less than or equal to 8. All right, well, we've done most of the hard work, but we're not quite home yet. We know what's happening with theta and with phi and with rho. So we need to write it all down. We're after a volume, because that's what it tells us. So our volume is the integral over our solid of 1. Well, that becomes, we're going into spherical coordinates because it tells us that, integral, integral, integral of 1 dv. And that's rho sine of phi, d rho, d phi, d theta, right? Like the song says. Theta, 0 to 2 pi. Phi, 0 to arc cosine of 5/8. I should have given myself more space. Rho, 5 secant phi to 8. And there we go. That's it. Because remember, we only have to set it up. We don't have to solve. And so there's the beautiful setup, and life is good. Nice! Suppose that R is the region in the first quadrant of the xy plane enclosed by the curves y equals 8, y equals 2x, and xy equals 4. All right. Find equations for the 3 boundary curves of the converged region in the UV plane under the change of variables u equals square root of xy, v equals square root y over x. All right. Now, we actually don't have to draw anything, but just for sanity, I'm going to go ahead and do a quick sketch. So we say, all right, we've got our curves. We have our y equals 8. So that's going to look something like this. And so I'll put y equals 8. We have y equals 2x. Now that's going to be a curve that's going up. And then we have xy equals 4. Now this is also the same as y equals 4 over x. Yes, true story. And so what's going to happen here? Well, that's going to come down, and I'm just going to make myself a note here. This happens here at 4, and by the time x equals 4, you'll see y equals 1, and so it's come down quite substantially, and in particular, it looks like this. Okay, so our shape, which we're converting, is this somewhat triangular shape. So here we have our region. Now, we don't need to know any of that. What do we need? Well, we need to know what are the formulas for the curves. You might say, well, where are those given? And they're given in the statement of the problem, right? We have y equals 8, y equals 2x, and this last one is xy equals 4. All right, well, let's talk about these curves. And, well, we'll start y equals 8. That's the first one listed. Might as well start there. Y equals 8. So, what do we see? Well, looking here, we see we can have a couple of things. If you just, there's a couple, there's so many ways we could do this, and I'm just like, oh, which is the right way to do this? And one way to do this is to say, okay, we really can say, look, u equals square root of 8x, v equals square root of 8 over x. And now the question is there a way to combine these that could eliminate an x? And we say, well, here it's like you have a square root of x upstairs. Here it's like you have a square root of x downstairs. So if you were to multiply them together, so u times v, you would get square root of 8x, square root 8 over x, the x's cancel. Square root of 8 times square root of 8 is 8. So y equals 8 really is uv equals 8. And in fact, if you look what we just did, in general, we can say the following. If you take uv, what happens? You get that u times v is equal to square root of xy times square root y over x, and the x's cancel, the y's combine, and you get y. Oh, okay, cool, that's nice, and all right. So that works in general. And by the way, similar thought process, if you run it through, says, what if I flip this second term? So instead of square root y over x, x over y. So you could do u over v, square root of xy times square root of x over y, and what would you get? You would get x. So one way to do this whole problem is to actually do this computation. Say, look, x is u over v, y is u times v, and now just everywhere where you see y, put u times v, everywhere you see an x, put u over v, and you're done. So that's one way to do it. For me, I like to say, let's see if we can't reason it out so that we don't have to do this solving, because it's not always so easy to solve. Okay, so anyways, we have, this is one of our three. Y equals 8. Y equals 2x. Okay, what can we say here? Well, so if we put in y equals 2x, and for u, we get the square root of x times 2x. Okay, for v, we get the square root of 2x over x, and we're like, wait, 2x over x, the x's cancel, and we say, so that means v is square root of 2. And we say, oh, we could have seen that easier, right? Because we could say, oh, this is y over x equals 2, and then v is in terms of y over x. All right, so there's another line, and now our last one, x times y equals 4. Now for this one, we're like, wait, xy, there's an xy. We can just go straight for it. U is square root of 4. Okay, well that's 2. I'm not even going to bother with v because I don't have any x's and y's left. And so this becomes u equals 2. So our three bounding curves in our uv plane are uv equals 8, v equals root 2, and u equals positive 2. There we go. That's it. That's the whole thing, because that's all we were after. Now, generally speaking, when I see these types of problems, the way I'm thinking about approaching them is to trying to say, okay, can I rearrange the variables here to match something nicely in terms of u and v? So the xy, I can spot that. Y equals 2x says, oh, y over x, I can spot that. The y equals 8 is actually the hardest one. And there I have to think about, okay, how can we combine things? But usually things should become simpler. That's the whole reason that we go through this process, is we want to end up with simple curves. So you shouldn't be like, I'm getting terribly complicated expressions. Because if that's happening, that's a bad change of variables. It's a bad substitution. So look for beautiful things. All right. Consider an infinite solid of uniform density covering the region between z equals 4 e to the minus x squared plus y squared over 2 and z equals 0. All right, find its center of mass. Now, the nice thing is whenever we see something that says uniform density, we can say, well, let's just pick it. Well, what should we pick? Let's pick something to make it easy. So we're just going to say density is 1. All right, well, cool. Now, what's the shape? Well, that's going to be a more interesting story. So let's think about what's going on here. And we can think about this. This is a solid three-dimensional thing. We have a clue of where we're going. we see we have this x squared plus y squared here. Well, that's telling us you better be thinking about cylindrical. All right, so we start thinking like, yeah, okay, I'm down with cylindrical. Let's do it. So what does this look like if we replace this? So this would be z equals 4 e to the minus r squared over 2. And all right, well, in terms of r and z, this is a famous curve. It's called the bell curve. Now, I'm just going to draw half of it because I want to think of this in terms of the RZ plane. It starts off at 4, and then it quickly goes down. Now, it doesn't go to 0 because it's going to go infinitely far, but it really gets to 0 fairly quickly, but never quite there. All right, so that's our basic shape in the RZ plane. You say, all right, now what are we going to do? Well, we're going to spin it and say, what's happening in 3 dimensions? So, what do we get in 3 dimensions? Well, we get essentially a 3-dimensional bell, right? And but it's quickly going to 0. So it's this, right? So there's this peak at 0, right, 4, and then it quickly goes down. Now, not the best picture, but it's enough for us to say one quick observation. Does this have any symmetry? Now, why do we care? Well, that can help us when we're talking about center of mass. We say, oh, well, sure. If we think about what's going on, we can spin it around the z-axis. So I say, oh, the z-axis, it has a symmetry. And that's a terrible sentence. I should say symmetrical about the z-axis. Well, what does that tell us? Well, it really tells us the center of mass is on the z-axis. And now that is helpful because it tells us that the x and the y coordinates for the center of mass have to be 0. So we are 2 out of 3 coordinates done. That's 2/3. What? And all we've drawn is just a rough picture. And we're already 2 out of 3 coordinates. Wow. But I bet you that 3rd coordinate might take us some time. All right, well, let's start thinking about how to find that 3rd coordinate. So really, all our effort here is going to be z bar. So how do we find z bar? Well, that's going to be a ratio. Downstairs is the mass. Upstairs, take a moment. Yes, it's the moment with respect to the xy plane. But what it really is we can say, look, downstairs, it's the integral over our solid of our density. Well, our density is 1. So it's integral of our solid of 1 dV. Upstairs, it's the integral over our solid of z, which is the distance, times density 1 dV. So we have 2 integrals to compute. All right, well, let's go ahead and do them both. So we'll start with the mass. Usually the mass is a little bit easier. So let's see what we have. We have full symmetry, so theta is going to be 0 to 2 pi. What about r? Well, we're going out all the way. We're not stopping. So 0 to infinity. What about z? Well, we're going to go from 0, which is the plane, up to the surface. So 0 up to 4 e to the minus r squared over 2. And then we have our mass, it's just 1. And then we have our r, dz, dr, d theta, right? This is our dv. Okay, now we're cooking. Okay, integrate with respect to z. r is a constant, so is 1. It's a great constant. And so we'll get r times z. And so, okay, 0 to 2 pi, 0 to infinity of rz. Evaluate that, z equals 0 to z equals 4e to the minus r squared over 2. And then we have, okay, this becomes 0 to 2 pi, and now 0 to infinity of 4r e to the minus r squared over 2. Now from here, like, this could be in danger, right? But it's actually in pretty good shape for us, because what can we do? Substitution. So we can say, look, let's let u equal r squared over 2. All right? That seems reasonable. Then what is du? Well, it's r dr. And we say, okay, well, what does this then become if we carry out this substitution? Well, it becomes 0 to 2 pi. Now plug in 0, you get 0. What about plug in infinity? Well, you don't really plug in infinity. You just say, well, what happens as you go to infinity? And the answer is you get large, so it's 0 to infinity. You might say, oh, so the bounds didn't change. Well, they did. What happened? These were r bounds. We're switching to u bounds. But what do we have? We have the 4 e to the minus u, and then the r dr becomes du. Okay, so this becomes integral 0 to 2 pi, and then we get minus 4 e to the minus u. Evaluate 0 to infinity. When you plug in infinity, of course, I keep putting in quotes here, you can't really plug in infinity. So when I talk about plugging in, I just really mean what happens as you go to infinity. So it's an improper integral, and the way you do improper integrals is what's in the limit. And so there's sort of a limit embedded here. E to the minus infinity is 0. It's going to get small. So this becomes 0 to 2 pi of 0, subtract, and then when you plug in e to the 0 is 1. So subtract a minus 4 makes 0 plus 4. Say, oh, okay, well that's fine, that's 4. So you get 4 theta, evaluate from 0 to 2 pi, which is 8 pi. All right, whew. Good, good. All that work is to say, hey, you see that dv integral downstairs, the one that gives you the mass? That's an 8 pi. So we're halfway to our z bar. Well, of course, halfway still means we have half to go. All right, so pick up another color, because now we're going to do another integral. So the moment integral. That's right. Our moment has come. So mxy. It's basically the same integral. All that happens is you add one extra thing, z. And because we're in cylindrical coordinates, we don't have to change any of our setup other than that 1 becomes a z. So we have integral 0 to 2 pi, integral 0 to infinity, integral 0, 4 e to the minus r squared over 2 of z r dz dr d theta. Okay, our setup is in place. Now we integrate. What happens? Well, see, last time we integrated 1, we got z. This time we're actually integrating z. So we're going to get something. So we're going to get 0 to 2 pi, 0 to infinity, and what will we get? We're going to get 1/2 z squared r. Evaluate z equals 0 to z equals 4 e to the minus r squared over 2. Okay, well, you plug in 0, you get 0. So you have to plug in this 4 e to the minus r squared over 2. What happens when you square that? Well, what's going to happen is you'll get 1/2, 4 squared, 16. E to the minus r squared over 2 quantity squared. Let's write that down explicitly. So we have that, right? Then when you have something to a power, you multiply the powers. Multiply these together, and you get e to the minus r squared. So in other words, the 2's cancel. So we get e to the minus r squared. All right, good. Now, what are we going to do with this integral? Same kind of thing we did over here. We're going to do a substitution. All right, well, what's our substitution going to be? Well, same kind of thing. We're going to let u, in this case, be r squared. So that du will be 2r dr. And the good news is we have plenty of 2's floating around. And so what does this become? Well, this becomes integral 0 to 2 pi. Now, plug in 0. 0 squared, 0. Plug in infinity. Infinity squared, infinity. Really think of it as big squared, big. All right. 1/2 times 16 is 8. From that 8, I'm going to take 2 of that 8 and join it with the r dr to get du. So I'm going to be left with 4, because 8 is 2 times 4. Okay, so that becomes 4. And what do we have? E to the minus u. And then what can we say here? Well, we have our du d theta. All right. Whew. Okay. Now, we can keep going, and we will, but I just want to make a quick observation. Does this integral look familiar? Like we've seen it before. What? It's the same integral. So I predict we'll get 8 pi. Let's find out. We'll go ahead. You know, we don't always get so lucky. It may not be the exact same. We may be off by a constant, but that's all right. So we integrate, and this will become minus 4 e to the minus u. Evaluate u equals 0 to u equals infinity. And we plug in infinity, we get 0. Plug in 0, we'll get e to 0 is 1, so we get minus 4. So it's really 0 minus 4, which just becomes 0 plus 4. Say, okay, well, that's really 4 theta, evaluated from 0 to 2 pi, which is 8 pi. All right, 8 pi. Okay, so we have 8 pi over 8 pi, which gives us a final value of 1. Okay. Now, we should put it all together because it says find its center of mass. So its center of mass should be a point, and the point is 0, 0, 1. And there we go. Now, you should ask yourself a question. Is 1 reasonable? And we can look in the RZ plane. That says 1 is roughly there. Is that reasonable? Well, actually, it's not bad, right? Because there's a lot of things happening near the origin. It gets pretty tall. But most of the surface, a lot of the solid is lying underneath. It's down low because we go out infinitely far. So it's not a bad guess. And it's not a guess. It's not a bad answer. What would be a bad answer? Well, what if we said 008 pi? Well, that would have been way, way up here. In fact, it would be so far north, I couldn't put it on the screen. And I should say, oh, wait, it can't be 008 pi. I must be missing something. And it's like, oh, yeah, I got to divide by mass. Oh, yeah. But there we go. Woohoo! Nice answer. You know, it's fun when you get a nice answer. And you might say, why did we do all this work to get the 1? But you can also look and say, like, wow, isn't that nice? That's beautiful. That's beautiful. Consider a solid sphere of radius 2 centered at the origin. Find the volume V of the portion of the sphere lying between the cone phi equals pi 6 and phi equals pi halves. All right, well, what's this look like? What's going on? So if we think about it for a moment, and we have beautiful symmetry, there's no theta involved, and when I see no theta involved, this makes things a little bit easier. So I'm going to start by looking at a slice. And essentially, I'm looking in the RZ plane again. So let's do this. We'll look here in the RZ plane. And what do we have? Well, we have a sphere of radius 2. So we can sketch that. And let me change colors. Oh, so many good colors here to choose from. Let's go with red. Okay, so we have our sphere of radius 2. And there we go. Then we have two angles. So one angle is pi 6, the other angle is pi halves. Now remember how we measure this angle. So this is phi. So straight up is 0, and then we increase. So pi halves is actually here. It's the xy plane. So here is our phi equals pi halves. Now where is pi 6? Well, pi 6, roughly 30 degrees, it's upstairs. So we're coming up to this angle. Phi equals pi 6. Now we want to be between these cones. And phi equals pi halves doesn't feel like a cone, but a cone has been really flattened. It's the xy plane. And so we say, okay, so it's this shape here. Now that's just a slice, and then what do? We spin it. So if you were to now spin this around, then we'd get our shape in 3 dimensions, which is a little bit harder to sketch perhaps. But what do we have? Well, we have this sort of inner cone here. That's this phi equals pi 6. We go out to a distance of 2, and then we have the sphere coming down, and we spin here. So we have cone, and then so that's our basic shape. All right, and cool. Now, how do we proceed? Well, we know what setting we're in, right? Because what do we see here? We see that we have things described using phi. So as soon as we saw a phi, it's like we know where we're going. We're going to be going into spherical coordinates because that's the only place where we see phi. So we say, okay, well, given that we're going into spherical coordinates, well, we need to describe things in terms of spherical coordinates. And the good news is it's not too hard to do that. So, all right, so our volume, that's going to be integral over our solid 1 dv. Okay, so integral, 1. So we're in spherical coordinates, so it's rho sine of phi, d rho, d phi, d theta, right? Now, theta, we're going full circle, 0 to 2 pi. Phi, it tells us, where are we going from? We're going from pi 6 to pi halves. Cool, that was easy. What about rho? Well, rho, remember we always start at the origin because everything relates back to the origin, and then we're going to go out till we hit our surface. So we go out to the sphere. So that's where we're going from. So we're going from the origin, which is rho equals 0, to the sphere, which is radius 2, which is 2. All right, good. And now we're like, hey, this is beautiful. Okay, so we can go ahead and integrate layer by layer by layer, and we'll get our answer. I'm going to do a shortcut here. And you might say, this feels like cheating, but it's not. Notice our bounds. Numbers. right? Number to number, number to number, number to number. Now, if this were in 3D, it's like, oh, it's like a box. Yes? And it is. And so if we're in the rho phi theta plane, our space, it is a box. Now, what can we do? Well, notice how we can pull apart the function. So it's something in rho times something in phi, and even we can think of something in theta as 1. So we can think of it, instead of like 3 nested integrals, it's really 3 separate integrals that we're going to do. So let's go ahead and do that, just for fun. If you don't like this, just do the normal integral. At this point, there's no surprises. So integral 0 to 2 pi d theta. And we can only do this, by the way, because we've got all numbers and our function easily separates. Pi 6 to pi halves sine phi, d phi, and 0 to 2 rho squared d rho. All right, so each integral needs to be done. All right, so let's do our theta integral. This is theta. Evaluate 0 to 2 pi. We get 2 pi. Integral of sine. Well, what's the integral of sine? The integral of sine is minus cosine. Okay, so this becomes minus cosine phi. Evaluate pi over 6 to pi over 2. Okay, cosine of pi over 2 is 0. Okay, cool. So we get 0, subtract, and then we get minus cosine of pi over 6. And cosine pi over 6 is, well, we have to think about that one for just a second. That's going to be root 3 over 2. Okay, and this is, it's nice to know your various tables. Okay, so minus root 3 over 2. Well, that's really a plus root 3 over 2. All right, good. We're making good progress here. And, okay, well, still one more to do, and that's what's the integral of rho squared? Well, all right, for that, we can say the integral of rho squared, that's 1/3 rho cubed, evaluate from 0 to 2, well, that's 8/3. And so now, multiply them together. 2 pi times root 3 over 2 times 8/3. Well, you can get a 2 to cancel, and so what do we end up with? We end up with, at the end, 8/3 times root 3 times pi. And there we go. We're done! We found the volume! Huzzah! Huzzah! Now again, if you don't like this, you don't have to do it. Just one layer at a time, and you'll get it. And we can only do it because we got really nice bounds. All right, well, another problem. Let's keep going. Let D be the solid bounded above by z equals 2 and below by z equals 2 times x squared plus y squared. With the density function, delta xyz is 7 over pi square root of x squared plus y squared. Find the moment of inertia of D, your solid, about the z-axis. All right, well, this is an inertia in 3D. Now, there's a couple of things to see. We see x squared plus y squared, and we're in 3D, and that's very suggestive. It's saying, hey, perhaps, maybe, just maybe, let's think about using cylindrical coordinates. Okay, we're cool with that. Now, what are our shapes? Now, x squared plus y squared, z equals x squared plus y squared, that's actually a shape we've talked about before. And that's, the fancy name is an elliptic paraboloid, but it's a bowl. So it's a bowl shape. And z equals 2 is a plane. So it's like, okay, in 3 dimensions, let me first sketch the axes here. In 3 dimensions, what do we have? It's a bowl that runs up to z equals 2. So there's our solid. All right, there's the shape. Now, what do we do? Well, we want to think about our moment, and sorry, I'm just organizing my thoughts here. I'm going to look in the RZ plane just to help make sure I understand what's going on. And so we have our z equals 2, that's our top. And then our bottom is z equals 2 r squared. So it's this parabola here, z equals 2 r squared. All right, now that's our shape here in the RZ plane. Now we need to think about moment of inertia. And it's the moment of inertia with respect to something. Because whenever we talk about moments, they're always with respect to something. So it's with respect to the z-axis. So let's for a moment take an arbitrary point. Let's say this is the arbitrary point. And now I'm thinking about, I want to find the contribution of this little tiny piece. Well, inertia is the sum of our distance squared times mass. All right? So I say, okay, I can compute the mass. I have ways to do that. What's the distance? Well, the distance would be the distance to the z-axis, which is represented here by this line. So I say, well, how far away is that? Well, the answer, r. So r, if you think in polar, you know, you have your space, you start at the origin and you move r away. So it's r is how far away you are from the origin. Well, in 3D, the origin becomes the z-axis, and so r is how far off the z-axis you've gone. So it's like, oh, cool. So that tells us that our distances are. Now, let's put this together. So what do we have? So we have our inertia. We'll put a z for z-axis. Is we're adding up. So it's a three-dimensional solid, triple integral. Distance squared, r squared. Mass. How do we find mass? Well, mass is density, which will become 7 over pi r, then times density times small bit of volume. So it's density dV. Now what is dV? R dz dr d theta. Okay, so let's make sure we understand where all these pieces came from. So here, this is the distance. Here, this is the density. Here, this is your dV. Density dV, mass. Distance squared times mass, that's inertia of that little piece. Now, bounds. Theta, 0 to 2 pi, because we're full circle. Symmetry all the way around. R, well, got to think about that. So, where do these two curves intersect? In other words, when does 2 equal to r squared? We say, aha, that's a 1. So we're going from 0 to 1. You might say, wait, what about -1? Well, we only want positive r. But how do we get that point? Well, that's where theta comes into play. Because what will happen is when we spin it around to the other side, we'll catch that side. Oh, okay, so we only do need positive r. So r goes 0 to 1. Now, what about our z? Well, z, given in r, we're going from below up to above. So we're going from 2r squared up to 2. Okay, so that's the setup. That's the hard part in many problems. It's like, can we get the setup? And then from there, it's just work it through. All right. well, so let's do the integral. 0 to 2 pi, 0 to 1. And now we have an r squared times r. And so we have 7 over pi r to the 4th. Okay? And what's going to happen next? We're integrating with respect to z, so it's times z, because there's no z's there. And we're evaluating from z equals 2r squared up to 2. Okay, dr d theta. All right, well, this is 0 to 2 pi, 0 to 1, and when we plug in 2, we're going to get 14 over pi r to the 4th, subtract, plug in 2r squared, and whoops, why did I say 14? 2, no, 2 is fine. 2 times that, and here, plug in 2, and we get another 14 over pi, and then r squared times r to the 4th makes r to the 6th. Whew, my goodness, what an expression. Okay, well, let's go ahead and pull that 14 over pi out. Okay, so we have a 14 over pi out in the front, because we can do that. We have the technology. And then we're integrating. There's not an equal sign there. The equal sign is there. Okay, 14 over pi, integral, 0 to 2 pi. And, all right, we've already pulled out the constants. Integral of r to the 4th, 1/5 r to the 5th. Integral r to the 6th, 1/7 r to the 7th. And now evaluate from r equals 0 to r equals 1 and integrate that with respect to theta. Well, the good news is these are nice numbers, 0 and 1. Plug in 0, you get 0. Plug in 1, 1/5 minus 1/7. And okay, well, you can put common denominator of 35. That's 7 over 35. Subtract 5 over 35, which gives us 2 over 35, which is a constant. So we can pull that constant out as well. So we have 14 over pi, 2 over 35, and then we have the integral 0 to 2 pi of d theta. Now 14 and 35 both have factors of 7. So if we simplify, and of course, who doesn't want to simplify? So pull out a 7 and divide. This is a 2 and a 5. And now we say, well, what's the integral 0 to 2 pi d theta? Well, that's 2 pi. So we have a 2 over pi, a 2 over 5, and 0 to 2 pi d theta. It's theta evaluated from 0 to 2 pi, which is 2 pi. All right, we'll go ahead and just make some notes here. This is theta evaluate from 0 to 2 pi. And now the pi's cancel. Ha ha, ho, ha ha. And we get 2 times 2 times 2, which is 8. And then divide by 5, 8/5. And there we are. We did it. We got an answer. And, all right. Well, phew. Good, good. Consider the solid region. No, I'm pretty sure they meant to say region. All right. That's okay. This is not an English class. Consider the solid region D in the shape of a hemisphere described by x squared plus y squared plus z squared less than or equal to 9 with z greater than or equal to 0. Okay, so top half of a sphere. Great. We like that. If the mass density for a point in the solid is given by density xyz, calculate z bar, the z coordinate of the center of mass. All right, cool. Well, so what's our shape? We have, it's the top half of a sphere of radius 3, right? Not radius 9, radius 3. And so, okay, it's a hemisphere. Now, we need to find z bar. Now, we've talked about z bar before, so let's just remind ourselves. How do we go about finding z bar? Well, it's a ratio. So z bar, it's an average, if you will. So it's the, well, it's the moment, xy, over the mass, and where the mass is the integral over our solid of our density. While up here, the moment, it's z, which is distance to our xy plane, times density. All right, so those are our two integrals that we need to do. Now we have to make a choice. How do we want to integrate? In other words, do we want to do it in spherical coordinates, or do we want to do it in cylindrical coordinates, or are we just crazy enough that we are going to be like, let's go and do it in Cartesian coordinates? And you always get the same answer. The question is how long of a journey it will take. Well, given the nature of this shape, let's go ahead and let's try spherical. I don't know if it's spherical or cylindrical is going to be easier, but we should pick something, and once we pick something, we go with it. Okay, now, when I'm thinking of setting things up, spherical or cylindrical, I always think about looking at a cross-section. So I'm here in the RZ plane, and this shape is really simple when we slice. It's just a part of a sphere, right? And so it becomes part of a circle. In this case, a quarter circle. So, all right, we've got our quarter circle. Hello, quarter circle. Great to see you. All right, now let's talk about bounds. Well, a couple of bounds are pretty easy. Theta, that's pretty straightforward because we're going to go fully around, right? We have this beautiful symmetry. So that says 0 less than or equal to theta less than or equal to 2 pi. All right, well, what about phi? Now, remember, phi is in relationship to the z-axis. So phi equals 0, you're pointing straight up. And we say, okay, so we're starting at phi equals 0. We've already are on our region. And then we just sort of pivot, 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 and then we stop. Where's that? That's at pi halves. We've got a quarter way around. So we say, okay, so that tells us phi is between 0 and pi halves. All right, well, what about r? Well, for r, what do? You start at the origin, and you just go out. Say, okay, well, how far do you go? We're going from r equals 0, the origin, out to hit the sphere. So that tells us that rho, I may have been saying r, I meant to say rho, goes 0 to 3. These are, there's a term for this, nice, because they're all numbers. We like it when our bounds are all numbers. It tends to portend, good times ahead, or at least relatively straightforward integrals. All right, well, we've got two integrals to compute, so let's go ahead and pick one. Let's start downstairs. We'll start with the mass. So we're going to set up our integral. Integral, integral, integral. Our density function is z. But wait, we're in spherical. So remember that z is rho cosine phi. So what we have density is rho cosine phi. Now our dv, that's density. dv is rho sine of phi, d rho, d phi, d theta. After you do this for a while, it just becomes automatic that you sing. All right, bounds. Theta, 0 to 2 pi. Phi, 0 to pi over 2. And then rho is 0 to 3. Now, we've mentioned this before. These are really nice bounds. All numbers. All numbers. And if you look at your function, you're like, oh, I can pull it apart into nice pieces. And like, yes, then let's do it. And so we're going to split this, instead of thinking of it as a nested integral with 3 parts. We're going to think of it as 3 integrals where it's just one single integral. And we can only do that in certain cases, including here. All numbers in the bounds, the functions can be pulled apart. So we have 3 integrals that we're going to do. Integral 0 to 2 pi d theta, then integral 0 to pi over 2 of cosine phi sine phi and d phi, and integral 0 to 3, and let's make sure we get all our rows. We got rho and rho squared, so that's rho cubed, d rho. All right, well, let's work that out. Okay, now the first one, integral 0 to 2 pi d theta. All right, yeah, that's theta from 0 to 2 pi, and that's 2 pi. Great. Life is good. How about the second one? There's a lot of ways we can do this. We can do trig identities, or we can do substitution. And I'm going to do a substitution because I'm kind of anticipating. What am I anticipating? I'm anticipating that we are going to have to do something soon, which is we're not, see right now, currently our density is z, right? And so we're integrating z. We're going to have to do a z squared. So it's like, in the next problem, I'm going to have to do a cosine squared phi sine phi. And so I want to do something where I can basically say, aha, same idea. And so here, let's do the following. Let's let u equal cosine phi. Then du would be negative sine phi d phi, right? Rid of cosine, negative sine. And so this becomes minus the integral 1 to 0, because cosine of 0 is 1, and cosine pi half is 0. And the minus will put the signs back in the right order, so don't worry, it's okay. It looks weird, but everything's good. And then this becomes u du. Well, all right, well that we can figure out. That's minus u squared over 2. Evaluate 1 to 0. Plug in 0, you get 0. Plug in 1, you get minus a half. 0 subtract minus a half is a half. All right, so that's that layer. Now this layer, all right, well, rho cubed is 1/4 rho to the 4th. Evaluate 0 to 3, and so that becomes 1/4 times 3 to the 4th, which is 81. Okay, so all together, we get 2 pi times a half, which is pi, times 81 over 4. So we can say that this all becomes 81 divided by 4 pi. All right. All right. Cool. Cool, 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 cool. Good, good, good. All right. Now, what do we do next? Our other integral. Right? Because that's not our answer. That's the mass. We still have to do work to get the moment, and then we can simplify. It doesn't hurt to double check, so I'm just making sure we got everything, got all the terms, got all our rows, got all our bounds, and yeah, it looks good. So, hey, let's go ahead and work on the next layer. All right, so what's our next layer? Well, switch to a different pen, different integral. So we're going to have integral 0 to 2 pi, integral 0 to pi over 2, integral 0 to 3, and then we have our z, and z is rho cosine phi. So rho cosine phi times our density, which is z, which is rho cosine phi, times our dv, rho sine of phi d rho d phi d theta. Again, we can split it up. Integral 0 to 2 pi d theta. Integral 0 to pi over 2 of cosine squared times sine. So cosine squared phi sine phi d phi. And then integral 0 to 3 rho to the 4th d rho. Okay, now, some of these are going to be very, very quick. Why? Because they're the exact same, right? This is still 2 pi, no surprises. Here, same substitution. U equals cosine, du is minus sine. So this is going to become minus integral 1 to 0. But now, u squared du. So that becomes minus u cubed over 3. And evaluate 1 to 0, which becomes 1/3. All right. Now, last one here. Well, that's 1/5 rho to the 5th. Evaluate from 0 to 3. And, okay, so that's 1/5 times 3 to the 5th. That's 243. I kind of regret writing this as 3 to the 5th is 243. Because we could, and I can come back here and just revise this. This is 3 to the 4th times pi over 4. And here, we can do the same thing, right? We can say what? Well, okay, so we have a 2 pi. That doesn't cancel. See, previously 2 canceled with half, doesn't cancel with anything. So we have 2 times 243, which makes 486 pi. Downstairs, we have a 3 times a 5, which makes 15. But we really can say, look, this is really 2 times 3 to the 5th pi over 15. Now, why do that? Well, because we're going to take a ratio, and if there's lots of 3's, we want to make it easier for us to spot, oh, hey, there's lots of 3's here. We get lots of cancellation. And so write it in a way that will set you up to get lots of cancellation. All right, so we're ready. So upstairs, we have our moment. So that's going to be 2 times 3 to the 5th times pi over our 15. Oh, you know what I just realized? We can cancel a 3. Ah, that makes me feel silly. 3 times 5. That's all right. This should actually be 2 times 3 to the 4th pi over 5. But that's okay. The 3 will cancel in a second here. Now, we're dividing by mass. Since we're dividing, multiply by the reciprocal. 4 over 3 to the 4th pi. Now, if we've lived a good, clean algebra life, I know we have, because, you know, we believe in algebra. It is the way. Okay, what should happen? Lots of simplifying. The pi's cancel, that's good. And if you count up your 3's, there's 3 to the 5th downstairs and 3 to the 5th upstairs. So, what does that leave us with? Well, it leaves us with 2 times 4 upstairs and 5 downstairs, or 8/5. And so that's the answer. We'll just write it down here so we can put it in a nice box. Z bar is 8/5. All right. Now, does that make sense? Well, where is 8/5? Now, if we were engineers, we'd say, oh, well, that's really 1.6000, right? 8/5. And so if you think about that, that's a little bit more than halfway. And you might say, oh, wait a second, does that seem right? Because there's a lot more shape below than there is above. That's true. But think about density. Where is the dense part? You see, the dense part, it depends on Z. So it's very sparse here, very dense here. So there should be a bit of a bias towards the top. So even though there's more shape below, there's more density above, and so it roughly balances. So actually, that's not a bad, looks like a bad answer. And so it's a reasonable answer. And we like reasonable answers. So, whew, good. Score 1 for reasonableness. Use spherical coordinates to find the following integral. Integral from minus root 3 to positive root 3. Integral minus root 3 minus y squared to positive root 3 minus y squared. Root 3 times x squared plus y squared to root 12 minus x squared minus y squared. 15z root x squared plus y squared dz dx dy. What? What is this? What is this? This is crazy. All right, well, let's start unwrapping it and see if we can't figure some things out. Okay, so we probably first need to figure out what this shape is. And so we'll start saying, what are our current bounds? So y, that goes from minus root 3 to plus root 3. And then x, that goes from minus root 3 minus y squared to positive root 3 minus y squared. Now, let's just pause here and think about this portion. When we sketch this, well, we're in the xy plane, so we have root 3, we have minus root 3, and then we have these surfaces, or sorry, these curves. What are they? Well, we can solve for one, right? X equals positive root 3 minus y squared, square both sides, x squared equals 3 minus y squared, or x squared plus y squared equals 3. Wait, that's a circle of radius root 3. Hey, that's something we can sketch. So this is the positive root 3 minus y squared. This is the negative root 3 minus y squared. Okay, so that tells us that our region we're integrating over in the xy plane is this circle of, well, radius root 3. But okay, we understand that shape. Now, let's think about our other portions, which are our z. So z goes from root 3 times x squared plus y squared and up to z equals root 12 minus x squared minus y squared. Now, if we're channeling our cylindrical coordinates for a second, and I know you're thinking, you're not supposed to channel cylindrical, you're supposed to channel spherical, but they're closer than you might think. You say, hey, x squared plus y squared, that's r squared. Square root of r squared is r, so this is z equals root 3r. Oh. Now, I'm going to come back to that when we sketch. All right, so what about this? Well, if we square, z squared equals 12 minus x squared minus y squared, or x squared plus y squared plus z squared equals 12, we say that's a sphere. And what sphere is it? Well, we can think about x squared plus y squared plus z squared equals 12. Well, that's really root 12 squared. Root 12 is 2 root 3 quantity squared. Okay, now, what do we sketch? We see there's really no theta dependence in these surfaces. In other words, it's the same all the way around. So if I can understand a slice, then I can spin and I get the shape. So that's why I want to understand things in the RZ plane. So, in the RZ plane, we have two curves. Root 3r, that says we're going up. So this is z equals root 3r. And now, this is a sphere in the RZ plane. That becomes a circle. And it's a circle of radius what? Well, of radius 2 root 3. And so then, okay, good, good. Now, what do we need to figure out? Well, one thing we'd like to figure out is where do they intersect? Okay, so we're going to think about that question in just a moment here. And we're going up and down. And what's going to happen? Well, in the RZ plane, this becomes r squared plus z squared equals 12. So suppose that we tell you that z is root 3 times r, because that's true at the intersection. So if we say that, then what we get is that r squared plus, here, z would be 3r squared equals 12. And that becomes what? 4r squared equals 12, right? Yes? Good. R squared equals 3. R equals root 3. Wait, what? Really? They intersect at root 3? Well, that's nice. And you might be saying, wait, why is that nice? Because think about what happens if you spin this. What are you forming? A circle of root 3. So, everything has perfectly aligned. This really, truly is our region, right? Because we're down in the xy plane, we're going over our circle of radius root 3. So that means we're exactly capturing this shape. So what do we really have? In 3 dimensions, we have the following picture. We have a cone coming up. So there's a cone. And that's essentially, the cone is this triangle piece here. So we have a cone coming up. And then at the top of the cone, we have a piece of a sphere. Not much of it, but a piece of it. And so this is our region. It's a cone with a sphere on top. All right. Whew. Okay. Good. Now that we understand our region that we're integrating over, we can make progress in working on our spherical coordinates. Okay. So, with that part out of the way, now let's start working on the rest of it. Well, we need to describe this in terms of cylindrical coordinates. Sorry, spherical coordinates. We spin around, full symmetry. So that tells us that theta goes between 0 and 2 pi. Now, I'm going to skip phi for a second because I want to do r. R, you start at the origin and you keep going out until you hit the sphere. And what's the sphere? Well, the sphere is rho squared equals 12, or rho equals 2 root 3. So 0 less than or equal to r, less than or equal to 2 root 3. Now, what about phi? We're going to start at phi equals 0. That's not so bad. So 0 less than or equal to phi, less than or equal to, where do we stop? Oh, the questions. So we're going to stop when we're in that direction. So we need to figure out this angle. All right, so let me draw this one more time. And where do we have space? We really don't have space anywhere, but that's okay. Let's pretend like we have space. All right, so we have this line coming up, which is z equals root 3r. And we've made some notes here. So we said we go out to root 3. And now let's see if we can't mark some things. So if z equals root 3r, what is this length here? Well, if r is root 3, then root 3 times root 3 gives us 3. And now, what is this length? Well, that's r. That's root 3. So, the question, what's that angle? So what do we know about this angle? Well, we know a couple of things. Actually, we even know the third side as well. I might as well write it down. What's this third side? That's the distance out to the sphere. That's 2 root 3. We know all 3 sides. And so, the question is, do we recognize this triangle? And if you don't, well, you can always say, pick your favorite trig function, since you know all 3 sides. And say, well, okay, what do I like? Maybe I like sine. Okay, great. Sine is fine. How do you find sine? Sine is the opposite over the hypotenuse. So sine of phi would be opposite, root 3, over the hypotenuse, 2 root 3, which becomes a half. I'm like, whoa, wait, sine is a half. I know I've seen that before. Yeah, you really have. What's the angle? Well, the angle that gives a half is pi over 6. So sine of pi over 6 is a half, so phi is pi over 6. And that makes sense. It looks like it's more of a small angle. And so we say, okay, so phi goes 0 to pi over 6. All right. So there's our description of our bounds. So we're ready to set up the integral, because we actually have to find this, right? Well, so we have integral, integral, integral. And now we have to figure these things out. We have 15 z. Well, what's z? This is rho cosine phi. So rho cosine phi. We have root x squared plus y squared. Now what's that? Well, that is r. Okay, so what is that? Well, r is rho sine phi. Oh, okay, so that becomes rho sine phi. All right, now dz dx dy is dv. What does dv become? Rho sine of phi, d rho d phi d theta. All right, so there's our updated the dv, updated the functions, our bounds, 0 to 2 pi, 0 to pi over 6, and 0 to 2 root 3. Whew, okay, all right. Well, we've already had a good workout. Now we just have to integrate this thing. And we're going to do what we've done on earlier problems, which is to say, but this is a nice region in spherical coordinates. Nice, because look at your bounds. All numbers. All numbers. And the function, you can pull that apart. Almost as if it was meant to be. Because it was meant to be. We planned this the whole time. So we're going to pull this apart and do 3 integrals. All right, so what are our 3 integrals? So this is going to be equal to, we'll pull the 15 out in front, and then we're going to have the integral 0 to 2 pi, and there's no theta terms, so it's integral 0 to 2 pi d theta. Now, for phi, integral 0 to pi over 6. We have a cosine, and we have 2 sines. So I'm going to write this as sine squared phi, cosine phi, d phi. And now, for rho, 0 to 2 root 3, we have 1, 2, 3, 4. Rho to the 4th, d rho. Okay, now we do each integral. All right, the first one, that's, let's get that low-hanging fruit. That's theta from 0 to 2 pi. That's 2 pi. Whew. Okay, good. Now how about this next one? Well, we see sine squared and cosine. So this suggests, let's do a simple substitution. Let's let u equal sine phi. And then du, derivative of sine, is cosine. And so, oh, well, that's nice. So what do we have? We have integral. Sine of 0 is 0. Sine of pi over 6 is a half. We did that before. And then we have u squared, right? Sine squared becomes u squared du. Okay, well, that's what? Well, u squared, integral that's 1/3 u cubed from 0 to a half. And so that's 1/3 times 1 over 2 cubed. 1 over 3 times 2 cubed. And we'll probably clean that up in a minute, but for right now, I'll just leave it as 2 cubed. Okay, now the last integral. Rho to the 4th. becomes 1/5 rho to the 5th. Evaluate 0 to 2 root 3. So that's 1/5 times 2 root 3 to the 5th. Or that's 1/5 times 2 to the 5th times root 3 to the 5th. Now, if you think of root 3 to the 5th, it's like root 3 multiplied together 5 times. Normally we don't write it out this way, but notice what we can do. We have a root 3 times a root 3 times a root 3 times a root 3 times a root 3. So that's a 3, that's a 3, and that's a root 3. So this is the same as 3 squared over 5 times 2 to the 5th times root 3. Okay, so let's put all of this together. What do we have? We have 2 pi. Oh, don't forget the 15. 15. 2 pi. 1 over 3 times 2 cubed. Then we have times 3 squared over 5 times 2 to the 5th times root 3. All right. Now, let's simplify if we can. Well, we have a 3 and a 5 and a 15. So those cancel. Whew. Okay. Now, what's left? Well, let's look at our various numbers here. We have 2's. So let's see, we have 2 to the 5th. That gives us 2 to the 6th. Downstairs we have a 2 cubed, so that gives us 2 cubed. And then we have a 3 squared. There's no more 3's for it to cancel us. 3 squared, a single root 3, and a pi. And, well, we can actually work that out. 2 cubed is 8. 3 squared is 9. 8 times 9 is 72. Root 3 times pi. And there we go. Ah, whew, nice. That was a non-trivial problem. That filled up a page. But okay, we understand the ideas. It's like, all right, we're given something in our Cartesian coordinates. Let's work on describing it, and oftentimes work in a slice. Slices are useful, and then figure out, okay, hey, this is not a bad shape, and has a really beautiful description in spherical, which is why it makes sense to switch to spherical. And now, once we did that, we say, okay, pull apart, work on each piece, put it all together. Life is good. We made it through. Woohoo! Yes! Use a change of variables to evaluate an integral over the region 2x minus y times x plus 3y dA, where R is the triangle with vertices 0, 0, 1, 2, and 7, 0. Okay, let's first start by figuring out what our region looks like. And one of the things is we have to use a change of variables, and so we'll figure out what change of variables to make in a second. So let's mark our points. We have 3 points. We have 0, 0. That's easy to spot. 1, 2, so over 1, up 2. Let's say this is 1, 2. And 7, 0. And let's say that's over here. So x equals 7, y equals 0. So our region is this triangle. All right. Cool. Cool, 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 cool. Now, what are we going to do here? Well, we can say the following. Let's think about the bounding curves, because I think that helps to understand what kind of substitutions to make. Because one of the things that makes this problem particularly interesting, or you might say particularly non-trivial, is they didn't tell you what substitutions to make. There's kind of a clue. I'll call it clue 1. Clue 1 is to say, hey, I'm looking for functions on the inside. And I say, well, there's sort of 2 natural functions showing up here. 2x minus y, x plus 3y. So that sort of gets my curiosity piqued. Now I want to look at the bounding curves to see, do I get some additional confirmation that these are good substitutions to make? So let's talk about these curves. One curve, this curve, is very simple. That's y equals 0. Well, it doesn't really fit into that dialogue, but that's okay. Let's look at the other curves. Now here I'm coming out from the origin, and so that says I'm y equals something, and well, what's my slope? Well, if I go over 1, I've gone up 2. So my slope, that's 2x. So that's y equals 2x. And then it's like, whoa, wait, y equals 2x looks a lot like 2x minus y. That's confirmation that that would be a good substitution, because it's part of the function and it's part of the bounds. It's a 2-for. Two wonderful suggestions. Now, what about here? Well, that one's going to be a little bit trickier, so let's think about the slope. This says we do what? We're going to go over, from 1 to 7 is 6, and we're going to go down 2. And so the slope here, that's negative 1/3. So that gets us y equals negative 1/3. And now I can plug in that point at 7. So x minus 7. So y minus 0 equals minus 1/3 x minus 7. Well, let's multiply by, say, 3. So 3y equals minus x plus 7, right, because I can distribute that. And this becomes x plus 3y equals 7. And like, whoa, wait, x plus 3y, again, that's more confirmation, because it's part of the integral in terms of the function, and it's part of the bounding curves. Okay, so we now have a plan. We say, all right, we know what our substitutions are going to be. So we have the following. We're going to let u equal 2x minus y, and we're going to let v equal x plus 3y. All right, so there's our substitution. Now, let's do Jacobian. So we're going to do the Jacobian, and so we're going to take our u sub x and u sub y, v sub x, v sub y, take that determinant, take the absolute value of it, and notice these are functions of x, y. So this is going to be times dx dy equals du dv. All right, so, well, what do we have here? U sub x is 2, u sub y minus 1, v sub x 1, v sub y 3. All right, so we have 2, 1, minus 1, 3. So that's going to be 6 minus 1 is 7. So we get 7. So that's our great aha, 7 dx dy equals du dv. Now we can use sophisticated technology called divide by 7 and say, all right, dx dy equals 1 over 7 du dv. If you want, you can say that. There's other ways to basically get to the same point. All right, so we found our substitution. We found how to handle dx dy. Because our substitution is basically linear, in other words, these are linear functions of x and y, we're going to get out very nice, just essentially dx dy is some multiple of du dv. So it's, you want to keep track a little bit of where the multiple goes. And so, you know, because what do we want? We want the points, of course. So we want to make sure we get all the points. Okay, so we can handle the function, and oh, we might as well do that. It's not going to take us very much space at all. We can just do it right up here, right? Because what do we have? We have 2x minus y and x plus 3y. We say, well, what is 2x minus y in terms of u and v? Oh, it's u. What's x plus 3y in terms of u and v? Oh, it's v. So our function is uv. Okay, great. Now, that leaves us with one more thing, right? Because there's three things. Every integral has three things. How you break up, and that's where this Jacobian comes into play. What the function is you're integrating, that's what we did here. And then the last thing is the bounds. So you have to make sure you get all three things. All right, so let's talk about our bounds. Well, we have three bounding curves. So y equals 2x. Now y equals 2x, we can write that as 2x minus y equals 0. That's this curve here. But 2x minus y equals 0 gives u equals 0. And we're like, nice. All right, then we have, let's do this curve. And we already wrote that. That's x plus 3y equals 7. And hey, x plus 3y, that's v. V equals 7. Nice again. Woohoo! Sweet! Okay, and then we have our last curve, which is y. And we're like, cool. It's y equals 0. Now, this one maybe isn't so obvious, but let's look at it. If we plug y equals 0 into both curves. So when in doubt, just plug in what you know. Well, we know y equals 0. So that says u equals 2x, v equals x. And then we're like, well, wait. If v equals x, I can replace that x. So this becomes u equals 2v. All right. So that's our third bounding curve. So let's see if we can now sketch our region. All right, so if we're in the u-v plane, what do we have? Well, we have u equals 0. All right, so that's this curve, u equals 0. Then we have v equals 7. Okay, that's up here. V equals 7. And then we have one more curve, which is u equals 2v, or if we're thinking about this the way we normally think about it, v equals a half u, and so we'll think of it this way, v equals 1/2 u. All right, well, that's our shape, and now there's our region. So essentially what we've done is we've more or less made it so that our triangle shape became a triangle shape. And you're like, whoa, but what does that give you? Well, it gives us a nice right triangle, right? It's not the wrong triangle, it's the right triangle. No. It gave us a simpler shape to work with is what it did. All right, so here we go. Our integral becomes integral. The function is u times v. The dA, which was dx dy, becomes 1/7 du dv or dv du. Now the question, which way do we want to integrate? And why that way? Well, looking at the setup here, we can do one of two things. We can slice vertically or slice horizontally. Now, I have a preference here to slice horizontally. The reason is I see a 0. When you can get 0 in your bounds, do it. The more often 0 is in your bounds, the better life is. And you say, well, okay, so what order does that correspond to? Well, that corresponds to the order of, we're going to go du, dv. Okay, so our bounds, where does v go from? We go from 0 to 7, so that's our outer layer. Now, where does u go from? Well, u goes from 0, and then all the way out to u equals 2v. 2v or not 2v? That is the question. Now, all right, this looks like a much simpler integral than the one we started with. And that's the goal. We want things to be simple. And all right, so let's just start working our way through. We have the 1/7. We can go ahead and pull that out. Integral 0 to 7. We're integrating with respect to u. So v at this stage is a constant. So we have 1/2 vu squared because we're integrating with respect to u. Evaluate from u equals 0 du equals 2v dv. When you plug in 0, you get 0. When you plug in 2v, well, 2v quantity squared is 4v squared. And 4 times a half gives us a 2. So that we can pull the 2 out. So that's 2 over 7, right? 2 squared times a half, pull the 2 out. Integral 0 to 7, v times v squared is v cubed. All right. Well, now integral v cubed is 1/4 times v to the 4th. And we're evaluating from 0 to 7. And, well, okay, what happens? Well, plug in 0, you get 0. Plug in 7, you get 7 to the 4th. So we can cancel a little bit here. So you get 1 over 7 times 2 times 7 to the 4th. Well, I can cancel off a 7. And so we get 7 cubed over 2. And 7 cubed, of course, we all know that. Say it together. 343. Right. Yes, of course. We all knew that, right? So 343 divide by 2. And there we go. Our lovely answer. Whew. All right. Now, no big surprises on this one, other than they didn't tell us what variables to use, but then use context clues. Look for pieces in your function. Look for bounding curves. And if you get both, that's a sign. It must be that way. All right. Well, let's keep going. Use a change of variables to compute the integral. Integral over a region, y e to the xy dA, where R is the region enclosed by xy equals 1, xy equals 3, y equals 2, y equals 4. All right. Well, let's think about what's going on here. And again, similar to the last problem, it says use a change of variables. So we're going to have to do a change of variables, but they didn't tell us what the variables are that we should be changing to. But we have some clues here. And what do we do? Well, let's sketch our region. So I'm going to first draw some axes here. And, well, what do we have? xy equals 1 looks like y equals 1 over x, because that's what it is. It's y equals 1 over x. So it's like, okay, so you have this y equals 1 over x. Now, xy equals 3 looks very similar, except you've just sort of stretched it up by a factor of 3. So this, we'll say here, is xy equals 1. Xy equals 3 will look like this. And so here's our xy equals 3. And then we have y equals 2. And y equals 4. And it doesn't have to be super precise, but that's a reasonable image. So it's a rectangle-ish kind of thing. And now we say, okay, so what kind of things are we looking for when we're thinking about substitutions to make? Well, we sort of have two things in the back of our head. We say, well, we want to make a substitution which is compatible with the pieces that we see in our function and compatible with our bounding curves. And we say, well, our two bounding curves tend to involve something that looks like xy or something that looks like y. So those would make natural guesses. And then we look at our function and say, oh, we have something that looks like xy and something that looks like y. And then we're like, that's a really good sign. We like these things. We should do that. And so we're like, cool, cool. Okay, so what do we do? Well, we do the following. And we say, okay, this is our substitution. We're going to let u equals y, v is xy. All right, now let's figure out our Jacobian. So we're going to take the absolute value of the determinant u sub x, u sub y, v sub x, v sub y. And let's go ahead and work that out. U sub x 0, u sub y, 1. V sub x, y, v sub y, x. And, well, take this determinant, you get 0, subtract y, but you're taking absolute value, so you get y. Now, what does that tell us? It tells us that y dx dy equals du dv. And this dA, this is acting as our dy dx, dx dy, however you want to say it. So it's like, oh, so this y here will actually get absorbed into the changing of our variables in the part of the d's, the breaking up part. All right, so now we sort of have the other part, right? So that y is accounted for. E to the xy, well, that's the part that we have to figure out for the function. So e to the xy, well, that's going to become e to the v. Okay, great. We can do that. And so that takes care of that part. And so we have these two pieces here. And now the bounds. Well, we write our bounding curves. Y equals 2, y equals 4. These are going to become, and u equals 2, u equals 4. On the other hand, xy equals 1, xy equals 3 is going to become v equals 1, and v equals 3. And now we're like, oh, well, that's really very slick. It's very clean. And so in terms of the UV plane, when we do our change of variables, what do we have? Well, we have u goes 2 to 4, and v goes 1 to 3. In other words, rectangle. Okay, so here we go. We have that the integral over our region of y e to the xy dA is going to be equal to integral, and y dA, that's going to become our du dv or dv du. Now looking at our bounds, it doesn't really matter which one we do. So let's say du dv. We've accounted for the y. The e to the xy becomes e to the v. Where does v go from? V goes 1 to 3. Where does u go from? 2 to 4. All right. And this looks like a really good integral. The kind of integral we'd like to take home to meet the family. So the integral with respect to u, e to the vu, evaluate u equals 2 to u equals 4. And we say, well, plug in 4, plug in 2. 4 minus 2 is 2. So this is really the integral from 1 to 3 of 2 e to the v. And we say, well, that's just 2 e to the v. Evaluate v equals 1 to v equals 3. And then we say, well, that's 2 times e cubed minus e. And we're done. We're done. We made it. We made it all the way to the end. Good. Good. Now, could we have done this in another way? And do we even need to really do substitution or change of variables? Honestly, you don't need change of variables to do this problem, because if you just set it up to integrate first as a dx dy, then you'll find out, oh, it's very clean. There wasn't a need for change of variables, but that's okay. It really was a practice. And so we got practice setting up, doing our Jacobian, making sure we know how to change our how we break things up. We have the rest of the function, got our new bounds. Life is good, a fun problem, a nice way to cool down and say, woohoo, we made it to the end, yes! And I hope you enjoyed the journey. And I know some of these problems can take a while, some are pretty quick. The more that you do, the more it'll become natural. And the more natural it gets, the more fun it becomes. I know you can do these things. I believe in you. Keep practicing. It will come. It will start to make sense. You will become a master of these things. Thanks for joining me, and I hope to see you again. Bye.